We are on IB 19 section D, and we're going to do D.1 on its own individual video. And this is on solids of revolution, which means we're going to be working in 3D, which can sometimes be hard to visualize since we have to visualize it, or we have to draw it in a two-dimensional figure. And D.1 is the disk method. I don't know if our book comes straight out and says it, but that's what it is. So let's imagine you have a function. I'll make up something kind of interesting. How about this? My typical looking function. And say I've got an interval from A to B. And imagine if I was to revolve this function about the x-axis. So I'm going to draw a little swirly there to show that I'm going about the x-axis. So if I was to revolve it all the way around the x-axis, around and around, like 360 degrees or 2 pi, then what I'm going to do is going to form a solid. It's called a solid of revolution. So to kind of get a sense of what this looks like, I'm going to reflect that curve about the y-axis, sort of, or the x-axis rather, so that I can draw the picture. So this is going to end up becoming kind of like a vase. If you can imagine that. So trying to draw a three-dimensional figure there. And our goal is to find the volume of that vase, or that solid of revolution. And the way we're going to do it is using slices. So I'm going to draw a representative slice. Just so you can kind of visualize this. So back here you don't see that edge of it. Okay, and what shape does the slice have? What kind of object is it? Well, it's a cylinder. So we're slicing up our solid of revolution into all of these disks, or these cylinders. That's why it's called the disk method. And if we could find the volumes of each one of those slices and add them up, we would have the volume of the solid of revolution. So we could do an estimate of that if we actually literally were to slice them and get, X number of slices, we could find their volumes and add them up. And that would give an approximation of the volume. But we're going to use calculus to get an exact volume. And as we know, instead of adding up the rectangles, if we take the integral, then that will give us the exact value. So we're going to integrate so this is going to tell us the volume of the solid will be the integral from A to B of the volume of each slice. So I need to find the volume of a slice, because I'm going to be summing up these volumes. And the slice is a cylinder, so the volume of a cylinder is pi r squared times h, right? Volume of a cylinder. The pi is a constant. What's the radius of my cylinder? Well, the cylinder is kind of on its side. If you think about from the center to here would be the radius. I'm going to use big R. And that radius is also none other than the function. So R in this case is actually f. So we're going to be squaring f. And then the height of our cylinder is the thickness, which is the change in x, or delta x. Now when we go to sum all these, so what we're really doing here is we're summing all these. That becomes the integral of pi f of x squared dx. The delta x is the dx, and the summation becomes the integral symbol when we have an infinite number of slices. So the volume will be pi times the integral from a to b of f of x squared dx. And that's the disk method. You might also see it written, like in the AP Calc book, we write it r squared dx. R for the radius. The IB book also writes it, I have to look. They use y squared, which makes sense. From a to b of y squared dx. So those are all the same thing. Okay, well, let's do one of these problems. So the first one is, we're going to do two examples, examples 10 and 11. Example 10, okay, we're going to have a line y equals x. And we're going to revolve it about, so we're going to revolve the line y equals x about the x-axis for x between, let's see, 1 and 4 is what they did in the book. I mean, we could make up our own, I suppose, if we wanted to. And then find the volume of the solid. So the first thing you want to do is, of course, a picture. And I'll put 1 and 4 on there. 1, 2, 3, 4. So really what we're doing essentially is we are revolving this area, this region, about the x-axis. So to get a nice picture of it, I'm going to reflect it. And we have this. And just for fun, since I like to draw, I'm going to draw the little figure so you can see what it's going to look like. It's kind of like a cone. I think there's a name for those, and I don't know what they are. They remind me of the things, you know, the elephants sit on, that they put their little legs on in the circus. And there is a name for that. But anyway, so the volume is going to be pi times the integral from, I'll just write the formula down, a to b of the radius squared dx. So in our case, pi, we're going from 1 to 4. Our radius is our distance from here up to the function, so that's just the function y equals x, or in this case x squared dx. So it sets up to a really pretty simple integral. We'll integrate that, so we've got pi out front. We're going to integrate x squared, x cubed over 3. And then we're just going to go from 1 to 4. So bring my pi down, put a big bracket, put 4 in there. 4 to the third, I'll just write it out. 4 to the third over 3 minus 1 to the third, 1 to the third over 3. So that becomes pi, and then 4 to the third is 64 thirds minus 1 third. That becomes 63 thirds, which is nice because I can do that in my head. That's going to go in there 21 times. So that's 21 pi units cubed. Because whether they gave units or not, I'm not sure. I'd have to look. Okay, so that's pretty straightforward. Let's do the next one. Example 10. Or was it 10? I don't think it's 10, it's 11, silly. Example 11. Find the volume of a solid formed. Volume of solid formed by the graph of y equals x squared for x between 5 and 0 about the x-axis again. So draw a picture. These are fairly simple ones. I mean, there definitely are ones that are a lot more complicated that you really have to have a picture for. But I'm still going to draw the picture so you can see how it's set up. So that we've got y equals x squared. And we're going from 0 to 5. And this one is going to, so we're about the x-axis again. I don't know that they're ever going to have you do it about the y. We usually do that in AP Calc. I'm not, since I haven't worked through the homework problems yet, I'm not sure. So I guess we'll find out. I didn't draw that too well. And then Here's our little representative slice, or we can look at the whole thing. I like to draw the figure so you can get a feel for what it looks like. So it's kind of like that. Hey, that looks like a Christmas tree stand. I guess it would be more circular. Volume is pi times the integral from 0 to 5 of the radius, which in this case is the function, x squared, and then that's squared. Remember, it's pi r squared dx. So make sure you remember you're doing, just think pi r squared, so make sure you remember that you're squaring that. So we've got the integral of pi x to the 4th dx. So when we integrate that, we're going to have x to the 5th over 5, going from 0 to 5. Bring the pi along. 5 to the 5th over 5 minus 0. So that's going to be 5 to the 4th. I do believe that's 625, because 5 squared is 25, 25 squared is 625. So 625 pi units cubed. And that concludes D.1.